In this example, we're told a homeowner wishes to design a pump and pipe system for watering her lawn. She connects the pipes and pumps so that she can fill a tank from a nearby pond as shown in the sketch. You may assume the system operates adiabatically. We should also say that we're going to assume it's also operating at steady state. So the first part of the problem is determine the minimum power per unit mass flow rate in units of kilojoules per kilogram required to operate the pump at steady state. Part B is prove that if irreversibilities are present, the temperature of the water in the tank will be larger than the water temperature in the pond. And then part C, if irreversibilities are present, the power per unit mass flow rate required to operate the pump will have a larger magnitude than the result found in part A. So parts A and C really are very closely connected. We're just trying to find the minimum power for part A and then show that if there are irreversibilities in part C, that the power will be larger. Okay, so this is the picture we're dealing with. The first thing that we'll do is just let's draw a control volume that we can use here. So let's see, the control volume will have surround the pump and pipe system. And in this problem, I'm going to choose the ends a little bit differently than what I've done in the past. Normally what I've done in the two previous examples is I finish the control volume at the inlet and outlet of the pipe. It's totally fine. We could do a similar thing here, but I'm going to choose a little different control volume in this example, and I'll explain in a moment. The control volume is going to do is it's actually going to go to the free surface of the tank and the free surface of the pond. So you can see it looks something like that. And then I'll call this my point 1 over here and this my point 2 over there. So they're actually at the free, this is what we call the free surface. The surface of the tank and the surface of the pond is what we call free surfaces. They're often given by, the symbol is often an upside down little triangle to show that that's a free surface. Now the reason I'm choosing those as free surfaces is because I know the elevations of those points well. You'll notice that down here where the pipe is, I don't know that elevation. So if I use that as my point right at the inlet, I wouldn't actually know where the elevation is. Similarly, I don't know the elevation of that point in the pipe there, but I do know the elevations of the top and bottom surfaces. I mean the pond free surface and the tank free surface. Now you'll notice that I drew these control volumes kind of in sort of an arbitrary manner here. What those control volumes are doing is they're actually following what are called streamlines in the fluid flow. A streamline is, you've probably all seen these car commercials. Let's say I've drawn a car here. You've maybe seen pictures of a car in a wind tunnel and they show some streamlines going over the car's surface, something like that, right? So you've seen those kinds of videos maybe on the web or on a television commercial or something like that. Those are examples, actually those are examples of what are called streak lines, but they're also the same as streamlines in this case. They're just showing how the fluid is moving in this particular case. Now, the reason I'm showing you this is they're showing the trajectories of the fluid. There is no cross flow of the fluid. There's no fluid going across the streamlines. The flow is always parallel or tangent to the streamline, so there's nothing going across it. The reason I show you this is because I'm drawing these surfaces here to be along streamlines so that there is no flow crossing in the streamline. So whatever comes in here, right near the surface of the tube, is just going straight into the pipe. Same thing over here. Whatever comes out here is going straight up toward the surface of the tank. There's no flow going across it. So it's like these ends are just extensions of the pipe. There will be some set of streamlines through which the flow goes into the pipe and out of the pipe. Okay. You'll do a lot of this sort of thing in fluid mechanics, in a fluid mechanics course, but I'm just giving you a little preview here. The other thing that I'll do right at the start is if I apply conservation of mass to this control volume, what you'll find is that the mass flow rate at 1 is equal to the mass flow rate at 2, just from conservation of mass. We know that if it's steady, one inlet, one outlet, the mass flow rate in has to equal the mass flow rate out. Even though we do have some mass flow rate, the velocity at 1 is very small, and the velocity at 2 is also very small. The mass flow rates are not zero. Remember that the mass flow rate is like the density times velocity times area. We can still have a very small velocity. It's not zero, but it's very, very small, as long as the area is really big. So if V is really, really small, then area has to be really, really large. And you can imagine the surface of a pond, the surface of a tank, those are really big areas. They're going to be moving up and down ever so slightly. You know, when you pump water out of a pond, the surface has to go down from conservation of mass. But it does so very, very slowly. The velocity is really small because you have such a large area. Same sort of thing with a large tank, right? So our kinetic energies at the inlet and outlet, right on the surface at 1 and 2, they're not zero, but they're awfully small. They're negligibly small. So that's an assumption we're going to make. All right. Well, we can go ahead and do our analysis to find what the power is going to be under these conditions. Okay, so let's go ahead and get started on that. Actually, what I'm going to do is I'm going to go all the way back to the beginning with the analysis using the first law. So rather than going for Bernoulli's equation, I'm just going to start from the very beginning. If I go ahead and apply the first law, let's write it out. The reason I want to do this starting from the basics is because I want to include the irreversibilities. So we'll write out the full form of the first law. By the way, I wrote the power going in. Let me change that to in rather than on. So I wrote this form of the first law with the plus power going in, and that's because I know that there'll be some power coming in to the pump. So I like to work with a plus sign. We're told that the system is assumed to be adiabatic, so there's very little heat transfer, so we'll make that term zero. As I just mentioned a moment ago, the velocities at the free surfaces will be very small, so the kinetic energy terms will be negligible. We can cross those out. We're assuming that it's steady state, so that side will be 0. And then what we're left with when we simplify it will be the power in. I'll divide through by the mass flow rate, just like what we did with Bernoulli's equation. Should be, that'll be H2 minus H1 plus G times, let's see, that'll be Z2 minus Z1. All right, so that comes from the first law. We have the specific enthalpy term and we have the potential energy term. And again, the kinetic energies are basically 0 because it's so small. The next thing that we'll do is we'll make use of the definition of the specific enthalpy in terms of internal energy. Remember, the definition of specific enthalpy is internal energy plus P times V. I'm just doing a different approach here, so that H2 minus H1 will be U2 minus U1 plus, and since we're dealing with an incompressible substance, I'm assuming that the water is incompressible, we'll just have V times P2 minus P1. So I'll just make a note of that, assuming the water is incompressible. What that does is it eliminates any need to include the changes in the specific volume. And since the water is incompressible, we know that U will be a function only of the temperature, so that U2 oops, let me, actually, I take that back for a moment. Let me just leave that as is for the moment. Let's just leave it there. So now we have H2 minus H1 is U2 minus U1 plus V, P2 minus P1. Let me then go back up to our picture and figure out what P2 and P1 are. Since points 1 and 2 are on these free surfaces, their pressures are both going to be the same as atmospheric pressure. So here's the atmosphere. So P1 and P2 are just atmospheric pressure. So that term will cancel out, and H2 minus H1 will just be U2 minus U1 in this case. All right. Let's go a little bit further. So the next thing I want to do is write out our expression. What I'm going to do now is, well, let me simplify this a little bit further, and then I'll move on. Okay, so here's where we are now. Part of the reason I want to do this is because I know that for an incompressible substance, the specific internal energy is a function only of the temperature. And I'll come back to that a bit later in the derivation, because I want to see how the temperature changes for this process. Okay, let's go a little bit further now. Let's apply the entropy equation to the same control volume. So let's write that out. Okay, so that's being applied to the same control volume. We said that this was operating at steady state. It's adiabatic. And we have one inlet and one outlet, so this term is just m dot S1 minus S2. So then when we simplify it, we get sigma dot is equal to m dot S2 minus S1. Okay. The S2 minus S1, since we're dealing with an incompressible substance, we know that S2 minus S1, if you go back earlier in the notes, that will be the integral of the specific heat from T1 to T2 C T dt over T, right? So that comes from being an incompressible substance. Right, so then sigma dot will be m dot times the integral T1, T2, C, T, dt over T. So one of the things that you'll see right away, just from the entropy equation, is if sigma dot is equal to 0, meaning it's internally reversible, then if the left-hand side is 0, then the right-hand side must be 0. So then that means that T2 must equal T1. So if it's internally reversible, then the temperature won't change. But if sigma dot is positive, meaning that it's internally irreversible, so we have some losses that occur, we have some inefficiencies, then we know that the right-hand side must also be positive, and that means that T2 then must be greater than T1. Right? So this is our, if you go back up to part B, prove that if irreversibilities are present, the temperature of the water in the tank, that's our point 2, will be larger than the water temperature in the pond, our point 1. So that comes directly out of the entropy equation. You can see that right here. Keep in mind that the specific heat is always a positive number, and the absolute temperatures are always positive numbers. So that's why if sigma dot's positive, then this integral must also be positive, and that means T2 must be greater than T1. Okay. So if we're dealing with let's go back to part A up here. The minimum power per unit mass flow rate, well, that's for the reversible case. So for the reversible case, we know that T2 is equal to T1, right? Well, if you go back to our first law expression, if T2 is equal to T1, then our U2 minus U1 must be 0 because it's incompressible and the internal energy is only a function of temperature. So we can then write W dot in for the internally reversible case, or M dot, will be just simply G times Z2 minus Z1. And I'll just make a note here, since U is a function of temperature and T2 is equal to T1 for this particular case. So this will be our minimum power that we have to put in, right? It'll be our minimum power, and you can certainly plug in the numbers for this. And what you'll find is that when you plug in those numbers, it comes out to be it'll be positive 0.0981 kilojoules per kilogram. So that's the minimum power per unit mass flow rate that we'd have to put in to our pump in order to pump from the lower reservoir up to the upper reservoir. Now let's consider the internally irreversible case. So when sigma dot is greater than 0. So when sigma dot is greater than 0, we know that T2 must be greater than T1. We proved that from the entropy equation. If that's the case, then you go back up to the first law. Since U is a function of temperature, and as T increases, we know that U must also increase. You know this from all the tables you've worked with. The internal energy goes up. So if T2 is greater than T1, then U2 minus U1 will be a positive number, so then the work will be larger than that for the minimum or internally reversible case. So let me just rewrite that equation down here. So this was U2 minus U1. I'm just rewriting the equation from before. Right? And we're saying that if sigma dot is greater than 0, then T2 is greater than T1, which then means that U2 is greater than U1, since U is a function of temperature only for an incompressible substance, which then means that U dot in per unit mass flow rate will be greater than what it would be for the minimum case, the internally reversible case. All right, so we've now proven all the various parts that we needed to in this problem. So we'll go ahead and end it there.